Chapter 1, Section 2. Matter is made of atoms. In this chapter, Feynman begins by talking about what statement carries the most information, what single sentence would be most useful to tell people that had not been through the scientific revolution. And he comes to the idea that it is the atomic hypothesis, the idea that everything is made out of atoms. On exploring this idea, he takes us on a journey into the microscopic world, starting with a droplet of water. So I'm going to use this pipette to take a sample of this pond water. So what Feynman described was that through a microscope, the pond water showed Paramecia, lots of little tiny microorganisms invisible to the naked eye. Feynman then asked us to imagine what happened if we magnify in on that drop of water. If instead of it being this large, we make it grow to 15 miles across, and those Paramecia were now the size of blue whales or more. Well, on this scale, the water would stop looking like water, and it would instead start to take on, he describes, a teeming appearance. This is when the movement of the atoms first becomes visible. In fact, Feynman then said, what if you magnified by another 250 times? At that scale, the picture would look like this, and he includes a black and white diagram in the lecture series. And with Feynman, he's very quick to point out when something is just a representation. And he points out how this as a model is limited. He says that to start with, that the atoms wouldn't be limited into a two-dimensional plane like this. They wouldn't have these hard edges. You wouldn't see them as billiard balls. Neither would you see them in the traditional chemistry colours of red and white. And that though there are here completely static picture, they would never be static. They would be in constant teeming agitation. Now, though the forces can't be drawn on here, there are forces between the white hydrogen atoms and the red oxygen atoms. And there's one molecule of H2O is attracted to the H2O molecule next to it. Now, that means that there are forces making it clump together. Those forces we might know as surface tension, or basically it's just the forces that hold water in the liquid state. Feynman says that if you had an apple and you grew it to the same size as the whole Earth, that its atoms would be about the size of, well, an apple. So the apples on Earth are, to planet Earth, about the same scale as the atoms are inside an apple. That which you just saw was some smoke jiggling around. And what is true with the jiggling of the smoke, and indeed the jiggling of the water molecules, is that that jiggling, that teeming motion, is what in old-fashioned language we would describe as heat. We'd now perhaps describe it as thermal energy and use heat to represent the transfer of that thermal energy. But Feynman uses the word heat to represent the teeming motion of all of those atoms. Now, when we raise the temperature of something, the jiggliness increases. That's to say that the actual teeming motion itself becomes more obvious because the motion of each particle has got faster. That bejiggling motion is representative of its temperature. The higher the temperature, the more it jiggles around. And he said that if you heated it further, then what would happen is the jiggling would get to an extent where some of those molecules could actually break free of the other molecules, and at that point the water would become steam. At that stage, that zoomed in view of the water would be different. Now, Feynman describes the state of matter when the molecules can break free of each other as steam. And we today tend to use steam to talk about an aerosol of water. So droplets of water suspended in basically the hot air. And that eventually, when they disperse down to individual molecules, we then call that water vapour. But we might, because Feynman does, just call it steam for now. In fact, when Feynman presents this diagram to represent the molecules of water in steam, he then goes to great lengths to talk about how this diagram is not accurate either. He points out that on this scale, the chances of catching 3 of those molecules in this box are almost 0. In fact, there are probably only this many of these molecules in this entire room on this scale. Now, when a substance is in its gaseous form, then it's like the air trapped inside this piston. And Feynman talks about a piston, and he says that what's going on in here is that the molecules are moving around free of each other at really great speeds. And eventually they run out of space and collide with the walls of whatever container they're in. And every time they do so, it actually creates a small force on the wall of the container. So much so that if you look at this piston, what's stopping the actual top of the piston just sliding down? You'd think under its own weight it should just descend into the bottom. In fact, when I take my hand off it, it pops back up. So what is making it pop back up? And what is making it resist the compression? Well, it's just the fact that some of those particles are colliding with the bottom of the piston as well. They are, at this stage, in equilibrium with the weight of the plunger. Now, all of those tiny little forces spread out over the area of the inside of this piston, it gives us the pressure of the gas that is inside. So Feynman was thinking about this gas, and he wondered about what would happen to the number of collisions that was occurring with the walls and with each other if the total number of particles went up. He imagined doubling the actual total number of particles in there. What he said would now be happening was there'd be twice as many collisions with the walls of the container. And if that was true, that it meant that the pressure would be proportional to the density. Twice as many particles in this volume would double the density. Twice as many collisions occurring would mean twice the pressure. Feynman thought that this idea that matter is made of atoms is something that helps us to explain some observed phenomena. This measures air pressure, and you can see 96.5 kilopascals. When I hold it in my hand, then you can actually see that it is going up. That increasing the temperature without increasing the density has in fact increased the pressure. So understanding that matter is made of atoms, how can we explain this? Why does the pressure rise as the temperature rises? Well, if we consider the movement of all of those atoms and that pressure is caused by the collisions between those atoms and the wall of the container, if those atoms are moving faster, when they strike the wall of the container, they're going to hit with more force. And hitting the area of the inside of the container with more force results in a higher pressure. Now there's another thing that Feynman found interesting about the idea that thinking of matter in atoms can explain. And he drew in the lecture series a piston like this. And you can see that this is basically what we have here. The piston can be used for compressing or decompressing a gas. But how, thinking about the atoms, can we explain how compressing the gas and putting it under more pressure causes a rise in temperature? And what is physically happening to the atoms in here for them to gain more kinetic energy from just being squeezed into a smaller space? Well, that takes a bit of imagination. You see, what's going on here is that the particles are colliding with all of the walls, including the piston. Now, if you imagine that this racket represents a piston, then a particle colliding with it is going to have only so much momentum change. Did you see that it came down and it bounced away at the same velocity that it came with, but just in the opposite direction? But now imagine that you're actually pushing the plunger down. As you push the plunger down, you're physically moving the surface that air molecule is bouncing off, and it has a different effect. What is happening is that basically the pushing of that plunger is giving all of the particles a little bit of extra velocity. Now, of course, the speed of these particles would be 400-500 meters a second, and the plunger would be only very, very small. But when you think about that additional velocity is being added to billions of the particles, that contributes a massive increase in the average kinetic energy, and therefore the temperature. If you imagine the plunger being withdrawn again, well, the velocity of the ball is going to be ever so slightly less after hitting a receding plunger, and so the temperature will be less. So if an understanding that matter is made of atoms helps us to understand the things we see in a liquid droplet of water and in the turbulent motion of a gas, does it help us understand what is going on in a solid? So now Feynman invites us to consider what happens when the water droplet turns to ice. Now, with ice, the crystalline lattice of the atoms means that there are very definite places that atoms can be, and places that atoms cannot. You see, in this crystal, another atom could appear just here, but it couldn't, say, appear just there. It has to fulfill its allowed position based on the repeating pattern of the crystal lattice. Ice, for example, like these two here, can't just stick together unless the atoms are exactly in the right place. What I would find trying to stick these together is that they won't, because of the positioning of the atoms on a scale that is far smaller than our eyes can see. But what if we blew our little tiny frozen water droplet back up to 15 miles again? He said that the position of the atoms here in the frozen lake would be determined by the position of the atoms right on the other side. For when this body of water starts to freeze, then the atoms can only fit together in their certain place, which means even though this is 15 miles from the other side, the atom could be here, but it couldn't be there. That every atom had its very special place. With that same water drop frozen, if we were to magnify it back up to that scale where the atoms were visible, we would see that the molecules of water had formed a hexagonal shape. Now, any additional molecules of water would have to attach to that following the pattern of a hexagon, to the point where, if we got to the point where the crystal was visible, that too must also be hexagonal. So here we can see the crystalline nature of water, that the hexagon shape has a symmetry that means if we rotated it 120 degrees we would find the same crystalline pattern. And also you'll notice the large gaps of air in between the crystal structures. This is one of the reasons why the density of ice is much lower than the density of water, resulting in ice floating and resulting in the water taking up a smaller volume once it has melted. So on the scale of the molecules, you can see there isn't really that much difference between the liquid water and the ice. However, the ice has this repeating hexagonal pattern that the water, when it is liquid, does not. If we were to increase the thermal energy, if we were to add some heat, then each of these atoms, free to vibrate a small amount on the spot, well, they could be given enough vibrational energy to move out of position. And as soon as they move out of position, the symmetry and strength of the structure is broken, and it becomes instead the disorganized, constantly moving and flowing liquid water. That brings us back to water, where we started. Feynman plays with the idea of taking away the vibrational energy. So if you removed all of that motion altogether, then what would occur? Well, this is the state of absolute zero, the point where the particles are vibrating at their absolute minimum. And he points out that that does not mean they have become stationary. It means that they have the minimum amount of motion that they can have. And he points at the example of helium. Helium can be reduced in temperature until the point where it becomes liquid helium. But the liquid helium itself will never ever freeze. It is a material without a solid state. At no point can you get rid of that final bit of vibrational energy in order for it to become a solid. All of these ideas, be it pressure, be it temperature, be it all of the things that we've explored in this video, they all are the consequence of understanding that matter is made of atoms.